rather than the sun. Perhaps most dramatic of all were the vents themselves, which soon acquired the name black smokers. As it happened, the Galapagos Rift vents were tame affairs compared with some of the other 200 vent fields discovered since, scattered along the ocean ridges of the Pacific, Atlantic, and Indian Oceans. Tottering black chimneys, some of them tall as skyscrapers, pump billowing black smoke into the oceans above. The smoke is not real smoke, but broiling metal sulfides invading the seawater, welling up from the magma furnace below, acidic as vinegar, reaching temperatures of 400 degrees centigrade in the crushing pressure of the ocean deep before precipitating in the cold waters. The chimneys themselves are composed of sulfur minerals like iron pyrites, better known as fool's gold, which settle out from the black smoke, amassing in thick deposits over wide areas. Some chimneys grow at startling rates, as much as 30 centimeters in a day, and can tower to 60 meters before crashing down. This bizarre and isolated world seemed to be a vision of hell, and came replete with brimstone and the foul reek of hydrogen sulfide gas emanating from the smokers. Surely only the disturbed mind of Hieronymus Bosch could have imagined the giant tube worms, lacking either a mouth or an anus, and the eyeless shrimp, swarming in countless multitudes on the ledges beneath the chimneys, grotesque as a plague of locusts. Life in the smokers doesn't just endure these infernal conditions, it can't live without them. It thrives on them. But how? The answer lies in the disequilibrium. As seawater percolates down to the magma beneath the black smokers, it is superheated and charged with minerals and gases, most notably hydrogen sulfide. Sulfur bacteria can extract hydrogen from this mix and attach it to carbon dioxide to form organic matter. The reaction is the basis of life in the vents, allowing bacteria to flourish with no direct input from the sun. But the conversion of carbon dioxide to organic matter costs energy, and to provide it, the sulfur bacteria need oxygen. The reaction of hydrogen sulfide with oxygen releases the energy that powers the vent world and is equivalent to the reaction of hydrogen with oxygen that powers our own lives. The products are water, as before, but then elemental sulfur, the biblical brimstone that gives the sulfur bacteria their name. It's worth noting that the vent bacteria have no direct use for either the heat or any other aspect of the vent beyond the hydrogen sulfide emitted. This gas is not inherently rich in energy. It is the reaction with oxygen that provides the energy, and this depends on the interface between the vents and the oceans, the juxtaposition of two worlds in dynamic disequilibrium. Only the bacteria living right next to the vents, drawing from both of the worlds simultaneously, can pull off these reactions. The vent animals themselves graze on the bacterial mats, in the case of vent shrimp, or nurture bacteria within themselves, as if tending an internal farm. This explains why, for example, the giant tube worms don't need a digestive tract. They're fed from inside by herds of bacteria. But the strict requirement to provide both hydrogen sulfide and oxygen gives the animal hosts some interesting dilemmas, for they must bring a little of the two worlds together within themselves. Much of the curious anatomy of the tube worms stems from this unyielding obligation. It didn't take long for the conditions in the vent world to register with scientists considering the origin of life, first among them the oceanographer John Barras at the University of Washington in Seattle. The vents immediately solved many of the problems of the soup, most obviously the problem with thermodynamics. There was nothing of the equilibrium about that black belching smoke. Having said that, the interface between the vents and the oceans would have been rather different on the early Earth, as there was little or no oxygen back then. The driving force could not have been the reaction of hydrogen sulfide with oxygen as in modern respiration. In any case, respiration at the cellular level is a complex process that must have taken time to evolve. It can't have been the primordial energy source. Instead, according to the iconoclastic German chemist and patent attorney Gunther Wechtershauser, that earliest engine of life was the reaction of hydrogen sulfide with iron to form the mineral iron pyrites, a reaction that occurs spontaneously, releasing a modicum of energy that can be captured, at least in principle. Wechtershauser came up with a chemical scheme for the origin of life that looked like nothing else. The energy released by the formation of pyrites is not enough to convert carbon dioxide into organic matter, so Wechtershauser hit on carbon monoxide as a more reactive intermediate. This gas is indeed detected in acid vents. He promoted other sluggish organic reactions with various iron-sulfur minerals which seemed to have outlandish powers of catalysis. And, for an encore, Wechtershauser and his colleagues managed to demonstrate many of these theoretical reactions in the lab, proving them to be more than merely plausible. It was a tour de force that overturned decades-old ideas about how life might have originated, conjuring it up in a hellish environment from the most unexpected of ingredients, essentially hydrogen sulfide, carbon monoxide, and iron pyrites, two poisonous gases and fool's gold. One scientist, on first reading Wechtershauser's work, remarked that it felt like stumbling across a scientific paper that had fallen through a time warp from the end of the 21st century. But is he right? Harsh criticisms have been levelled at Wechtershauser too, in part because he is a genuine revolutionary, overturning long-cherished ideas, in part because his haughty manner tends to exasperate fellow scientists, and in part because there are legitimate misgivings about the picture he paints. Perhaps the most intractable failing is the concentration problem, which also afflicts the idea of a soup. Any organic molecules must dissolve in an ocean of water, and so are highly unlikely to ever meet each other and react to form polymers like RNA and DNA. There is nothing to contain them. Wechtershauser counters that all his reactions can take place on the surface of minerals like iron pyrites. But there is a difficulty with this too, which is that reactions cannot run to completion if the end products are not released from the surface of the catalyst. Everything either gums up or dissipates. Mike Russell, now at the Jet Propulsion Laboratory in Pasadena, proposed a solution to all these problems in the mid-1980s. Russell is a kind of prophetic scientific bard, prone to incantations of geopoetry, and has a view of life rooted in thermodynamics and geochemistry that seems obscure to many biochemists. But over the decades, Russell's ideas have attracted a growing band of supporters who see in his vision a uniquely workable solution to the origin of life. Both Wechtershauser and Russell agree that hydrothermal vents are central to the origin of life. But beyond that, where one sees black, the other sees white. One postulates volcanism, the other its antithesis. One prefers acids, the other alkalis. For two ideas that are sometimes confounded, they have remarkably little in common. Let me explain. The ocean ridges, which host the black smokers, are the source of new, spreading sea floor. From these centers of volcanic activity, the rising magma slowly forces the adjoining tectonic plates apart, the plates creeping away at the speed of growing toenails. As these inching plates collide with each other, far away, one plate is forced to plunge beneath another, while the other is thrust into petrified convulsions. The Himalayas, the Andes, the Alps, all were thrown into relief by the collision of tectonic plates in this way. But the slow movement of fresh crust across the sea floor also exposes new rocks derived from the mantle, the layer beneath the crust. Such rocks give rise to a second type of hydrothermal vent, very different to the black smokers, and it is this type of vent that Russell himself champions. This second type of vent is not volcanic, and there's no magma involved. Instead, it depends on the reaction of these freshly exposed rocks with seawater. Water doesn't just percolate into such rocks, it physically reacts with them. It is incorporated into them, altering their structure to form hydroxide minerals like serpentine, named after its resemblance to the mottled green scales of a serpent. The reaction with seawater expands the rock, causing it to crack and fracture, which in turn permits further seawater to penetrate, perpetuating the process. The scale of such reactions is astonishing. The volume of